Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And in this module, we are trying to understand how the operating system manages the CPU by providing this abstraction of a process, right? So within this second module, we are currently on the second topic, that is process address space, and we are now coming to the end of this topic. So basically, in this topic, we understood what is the process address space and what are the different sections in the address space, right? So now in this summary video, I'm going to briefly conclude all that we basically go over all that we learned in the previous videos. Just take a brief look at what all we have studied, what all we have covered, and summarize everything in this video. So let's get started without further ado. So we started this topic. The first video of this topic was an introduction to the address space, right? So here you can see this slide summarizes the concept of virtual address space. So we studied that this is the physical memory and it is forbidden. Basically, the processes, as you can see, they cannot access this physical address space. So the physical memory contains all of the data, and what the operating system does is that it provides each of these processes with their own virtual address spaces, right? A collection of addresses which only this process can access, right? And through this virtual address space, they get to see the physical memory. Each of the process has its own unique address space and its own view of the memory, right? Each process thinks that the memory is private to it via this concept of address space, right? So this is the concept of virtual address space. And then we said that this virtual address space or the process address space helps to organize the code and data for the process in the memory, right? So the memory, as you can see, contains the code and data for each process, and this process address space helps the process to organize it in a way, right? It has different sections. So code goes into the instructions, go to one section, different types of data go to different sections. So each of the different sections has its own purpose, and it all of them come together to enable the execution of the program, right? So now then in the second video, through basically now we looked at the code section, right? In the subsequent videos we have looked at each of the individual sections one by one, and in the second video we looked at the code section, right? So the code section, as you can see, there is a source code, and when you compile it you get a program. The program is a bundle of the instructions and the data, and your instructions, which are in the binary format, they go into the code section. So this section is purely for the instructions, and all the other sections store some kind of data, right? So this was about the code section. Then the next two videos focused on the stack section, right? So in the stack section, first of all, we understood why do we need the stack section. We studied that the stack section, the purpose of the stack section is that it is required for the execution of functions, right? So we studied that if you look carefully at the execution of any program, then basically, first of all, your program, as you can see here, is a collection of functions, and your program execution is basically a sequence of function calls. And the property about any sequence of function call is that it follows stack behavior. That is, as you can see in this change, this is the example of the factorial that we took in that video. You can see in this chain, the first function that returns in this sequence was the last one to be called, so which is last in first out behavior, which is stack behavior. So the function calls which are part of the sequence of the chain, right, they basically display stack behavior, and that is why we need the stack section in order to replicate this behavior. So we need the stack section for the execution of function calls, right? And then we in the next video we talked about stack frames, that is how are these function calls actually implemented on the stack, which is something using a stack frame. So as you can see, for every function call, a stack frame is pushed onto the stack, right? You can see three function calls. And what is a stack frame? The stack frame is actually a it's a collection of all the relevant pieces of information that is required to represent that particular function call. So not the function, the function call. So any instance of a function call is represented by the stack frame, and as you can see, the stack frame consists of several objects like the arguments to the function, the local variables, the return address, and a pointer to the stack frame, the previous stack frame, right? There can be many more objects on the stack frame depending on what all is required to represent that function call in that particular system. So this was about the stack frame. And then we saw how the stack frames with different examples, we saw how the stack frames are pushed onto the stack whenever a function call is made, and how when functions return, the stack frame is popped. So we understood the execution of the program using the that is how the program is executed, how the function calls happen using these stack frames, right? Then we took a example. So this code execution example, here we took a piece of code which was written in high level language like C, and then we compiled it to get the assembly code. So we said that the assembly code is tightly coupled with the execution on the stack, right? The ultimate execution, the final execution of the program has to happen on the stack, right? So as you can see, we talked about this in that video. It was a very detailed, a bit complex video also, right? So the assembly code that is generated has the code to create the stack frame, right? The first few instructions are required to create the stack frames, and then destroy the stack frames, and in between all of the instructions that are there, they in some way create some local variables, enable the execution, they pushing the arguments, having the return address, all of that mechanism that will actually happen on the stack. The assembly instruction has the basically instructions of how to actually do that, right? And through that example, we were able to see how the execution actually happens on the stack frame. We took this example, and by going over the assembly code, we saw a detailed example of how exactly instruction by instruction it happens on the stack section, right? So this was a detailed example which kind of summarized the stack section, the usage of the stack section, and how it is tightly coupled with the assembly code, right? Then before starting the data and the heap section, we said that we need to understand what is static and dynamic memory allocation. So as a prerequisite, we talked about, we understood the difference between static and dynamic memory allocation, because as you can see, it is required to understand the data and the heap section. So we talked about the static and dynamic memory allocations in detail and the differences between them. So static memory allocation is basically when the size of the memory remains fixed during the execution, and the opposite is true for dynamic memory allocation. That is, the size can vary during the program execution, right? So once we developed this understanding of what is static and what is dynamic memory allocation, then we looked at the data section. So we know that the data section consists of several objects like global variables, static variables, constant values, and all of these, the common thing among all of these data objects is that all of them are statically allocated, right? The size of each of them is known at compile time only. And through a piece of code, through an example, you can see we have global variables, static variables, constants, and we saw how all of these are placed on the data section and how they are used. So this example gave us a flavor of how the data section is used when the program executes, right? So here we saw the static memory allocation. Next, we looked at the heap section. So we know that the heap section is a basically the purpose of the heap section in the process address space in the memory is that it is used for dynamic memory allocations, right? Whatever are the runtime requirements, the memory requirements of your program during the runtime, all of them are taken care of from the heap section. Any dynamic memory allocation happens from the heap section. So this example that we took, right, you can see the malloc function, the free function. We saw how the programmer has to explicitly allocate and deallocate whenever they want to use dynamic memory. And through this piece of code, we saw how the heap section works. And in that video, we also talked about what is a memory leak, right? Basically, if you do not, if you forget to deallocate your memory on the heap section, then that is kind of a memory leak, right? You cannot reuse that piece of memory. So as a programmer, when you're writing a program where you're explicitly allocating memory, then it is your responsibility and you have to be careful that you properly deallocate those memories. Otherwise, they will basically there will be a memory leak and you will not be able to reuse that piece of memory, right? So this was about the heap section, the dynamic memory allocation, memory leak, all of those. And finally, in the previous video, we compared all of the different sections, the stack, the data, and the heap section. We saw a complete example where all the different sections were being used. So here you can see the global variable in the data section, the stack section containing the function calls, right? And the heap section also having a memory object. So this was in a way basically a complete example to illustrate you how all of the different sections you are used during the program execution. And finally, we also compared the different sections. Apart from the code one, we compared the different sections we store our data, what is the purpose, what kind of data goes in which section, how's the allocation and deallocation for all of these sections look like, right? So this was about the previous video, and here now we are summarizing all of that which we learned through this topic. So now we have completed this topic, right? Process address space is now completed. Our second topic is done. So now in the next topic, that is the third topic, which is system calls, exceptions, and interrupts. Here we will talk about process execution in more detail, right? So you can see in the first topic, the process introduction, we had a like we discussed in detail what exactly is a process, how we represent a process, how is it different from a program, what are the like what is the life cycle of a process. All of those things we discussed and developed a, first of all, a basic understanding, a good understanding of the process. And in the second topic, we developed an understanding of the process address space, which is very important when you talk about a process. In order to understand the process, we need to understand how does the memory look like for each process. So we by going over the process address space, the different sections, what are the purpose of each section, how is the memory allocated in each of these sections, we now developed in this topic a good understanding of how the process views the memory, how the code and data is organized for the process in the memory, right? So now we can say we have a good understanding of the process and its memory. And in the next topic, we are going to look at what all happens in detail during the life of a process. We will study system calls, exceptions, and interrupts. Basically, all of these are different mechanisms via which the process can interact with the operating system, right? Till now, we have not focused much on the operating system part, right? When I say the operating system part, I mean the actual interaction of the process with the kernel, right? So we have understood what is a process. Now we'll see how it interacts with the operating system in different ways during its lifetime. So guys, this was it for this video. In this video, we summarized all that we learned in this topic, that is process address space, and we can formally conclude, we can say that this topic is done. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.